Questions for Tobin, please take them into the chat room. Our next talk is by Elise Rumpf from the University of Hawaii Institute of Geophysics and Planetology. Elise is going to be speaking to us about experimental investigations of lava-regolith heat transfer. Elise, do you have your camera on?
I'm looking for it. It's right here. Okay, turned it on. Maybe taking a second. Oh, there we go.
Great. Thanks. Thank you. Okay, we'll give you a 2-minute warning.
Okay, thank you. All right, so this research is part of a project that I've been working on for my PhD with my advisor, Sarah Faden, and with Christopher Hamilton. His PhD with Sarah a couple of years ago and now has moved on to NASA Goddard. So this project stems from an idea that Sarah had originally been working on with Ian Crawford and Katie Joy about looking for extralunar particles in Paleoregolith. So when regolith deposits were brought back from the Apollo mission, they contained solar wind, solar flare, and galactic plasmic ray products. We've heard about this already during this session, and we're able to extract these particles. Now, there is potential, actually, on the moon to find some really interesting history about the sun on the moon, because on the Earth, there's a lot of resurfacing. We don't have really ancient particles, but we do have these ancient particles on the moon because it's been essentially geologically inactive for a very long time. So if perhaps we had an ancient Paleoregolith that was exposed to the lunar environment for an extended period of time and then was covered up by a lava flow, we could potentially go back to the moon and dig out underneath this lava flow and extract some extralunar particles from this Paleoregolith and learn a little bit about the solar history. So a lava flow would be a great barrier because it's going to protect that Paleoregolith from further bombardment, and it's also going to provide solid rock for radiometric dating. So if we did go and drill, we'd be able to date the lava flow beneath the Paleoregolith and the lava flow above the Paleoregolith and know exactly when this one little packet was exposed to the space environment. Now, one problem with covering something by a lava flow is that the lava flow is going to heat it up. And when the lava flow heats up the regolith, it's going to volatilize and destroy a lot of these particles that we're looking for. So this project has been looking at how much a lava flow is going to heat up the regolith and whether it's even feasible to go back to the moon and look underneath a lava flow for these deposits. We've done a lot of extensive numerical modeling looking at how a lava flow transmits heat into the substance, or into regolith particularly. I'm not going to go into that in depth here, but we just published this in JGR if you do have more questions about that. But overall, we found that a 1 meter lava flow, which is on the lower end of the thickness of lava flows that we think occurred in the mare on the moon, but a 1 meter lava flow is going to volatilize products to about 0.2 meters in the regolith. So that's, so you would need some significant development of regolith between lava flows, but that's still not that deep, and that's because regolith is very insulating. It's a very fine particulate, and so it's not a very effective transfer of heat. And so you don't get very deep heating from the lava flow because the regolith resists that heat pulse. Now, one of the limitations of our model is that there aren't many measurements of thermal conductivity of regolith and other particulate materials at high temperature. So one thing that we wanted to do was validate our models. And so our first idea to validate the model, since we live in Hawaii, we went over to the Big Island. And we had these great plans. Let's see, the slide's taking a minute to progress. Oh, okay. Well, my session has crashed, so I will reload it.
Yeah.
Yeah, so I'll try to reload this and I'll keep talking. So we went to the Big Island. We had this great idea that we could build a box and fill it with lunar regolith stimulant, and then embed that stimulant with thermocouples and put it in the path of an oncoming lava flow. Okay, let me see if I can get this going. There we go. Great. Okay, I can see me again. Great. Yeah, so we built this box out of calcium silicate insulation, which is this very, it's lightweight, it comes in sheeting, it's 1 inch thick, and you can just cut it with a bandsaw. So we cut it up. Build these boxes. We were actually able to embed it with, for this time, our lunar regolith stimulant was just some cinder we bought at the hardware store, something cheap. And so we went to the Big Island. You can see that picture there is myself and my advisor, Sarah Fagan. And we were able to successfully deploy this device in front of a lava flow, and we set up stereo cameras and a flare to get some information from it. Oh, okay, well, I'll just keep talking.
What happened?
Elise, we can advance your slides. I'm not sure if you're wireless or why you dropped, but we can advance slides.
Yeah, is it coming in and out? I'm not sure. Okay, so is it on the experiment, the field experiment still?
I think we're one slide behind because you said it was a picture of you on the lava flow. We never saw that.
Yeah. Okay, yeah. Oh, here we go. This one with the field attempts. Okay, now I can see. Okay, let me get my webcam going. Sorry about this, guys. Okay. So here, yeah, we have myself and my advisor, Sarah Fagan, and you can see this lava flow coming towards us. And so we successfully buried the box. Unfortunately, we didn't get any data, which we were kind of expecting because we didn't have fancy high-temperature equipment, and all that destroyed the instant that the lava touched it. But it was a really great proof of concept that we could, if we wanted to, bury some regolith stimulant, and with the thermocouples that were embedded in it, try to measure the heat transfer from an active lava flow into the regolith. Now, because we had some success with this, but there were definitely some limitations, we decided to try to do a more controlled experiment. And so we did this in the art department at UH. Luckily, I had a roommate who was a master's student in sculpture. And so she uses these big furnaces to melt iron and bronze to make sculptures, and she invited us over to use it to melt lava. So we collected a large kilolay of the salt and went over to the art department. We built boxes out of this calcium silicate material and embedded the bottom 15 centimeters with regolith stimulant. And this time we got GSC1 from Goddard. So we embed the bottom, or we pack the bottom with the stimulant, we embed it with thermocouples, and then we melt our kiloway of the salt. And we set up, we have the thermocouples measuring the internal temperatures, and there's a flare monitoring the external temperatures, and we also set up video cameras. And so here's a video from one of our pours. You can see the foundry in the back. That's me and Jen. The initial temperature of the lava is about 1250 Celsius. It's kind of, yeah, it is. And when you get up close, you can see how active this lava is. And part of this is volatiles coming out of the lava, and some of it is volatiles coming out of the regolith. We tried very hard to dry the regolith and to dry the box in an oven at about 110 Celsius for days, but no matter how hard we try, there's always a little bit of atmospheric moisture that gets in there, and that causes a lot of this activity in the bubbling. So we are also able to use a FLIR, and this is set up a little bit. You can watch here on the right, that's a dynamic temperature scale in Celsius. The red is always the hottest temperature, and blue is always the coolest temperature. And so here's our lava pour again. The maximum temperature is about 1250 C in the beginning. And you can see that activity right there on the surface. The redder areas are the areas that stay active longer because that surface is continuing to break and stay active. And the cooler colors are cooler areas where bubbles have formed and are sustained. So yeah, one more time. So we've been able to get some pretty good results from these. So this is what we end up getting from here. This is log, sorry, the bottom scale is not there. That's log time in seconds on the bottom. And then this is temperature in Celsius. So each one of these curves represents represents a temperature at one of the thermocouples. The top one is in the lava, so that's actually measuring the lava temperature. The green one, the second one, is at the this is at the Lava-Regolith boundary. So this is measuring the boundary temperature between the two materials. And then each of these below it is just progressively deeper within our 15 centimeters of regolith. So half a centimeter, 1 centimeter, and so on. A couple interesting things to note here. You see first our thermocouple kind of maxed out over here. This core was actually above 1300 Celsius, but our data logger only measured up to 1300. So you get a little plateau there, but it doesn't affect our overall results. A couple other interesting things that we see right here. So this is in our lava, and at our boundary we see some delayed cooling. You see these bumps where the cooling actually kind of plateaus for a little while, and it seems to have stopped cooling. And this is, we're pretty sure, is due to crystallization. So as the block of lava is cooling, it's crystallizing, releasing heat, and so it's actually adding more heat to the system and delaying the overall cooling of things. Another interesting little feature are these shoulders. We see these shoulders that delay the heating. They show up at about 80 to 100 Celsius, and we're pretty sure that's just the from the vaporization of any moisture that's in the system. So we've been able to get a pretty good numerical solution from our...
Elise, you have about just a minute or so left.
Okay, perfect. Thank you. So what you're looking at here, you can see it in the diagram. This is kind of a cross-section of the box. Within it, I'm going to play a movie and it'll heat up. So the cross-section of our experimental box, this fine grid here is the box itself. The blue is the cooler regolith at the beginning, and the red is the lava, the hot lava at the beginning. The outside is some air, but that can be ignored. But this is just a representative of about the first 2 hours of cooling, of heating of the regolith. The lava's cooling, the regolith is heating. Sorry if you can't see it perfectly. Yeah. So what's really interesting to note, if you can see the movie, is that inside the regolith, even after 2 hours of cooling, the core of the regolith is still very cool, even though it has this very hot lava heating it up. After 2 hours, the core of that regolith has seen the heat pulse very, very lightly, and that's because of this insulating property of regolith.
But others, this is a new feature when they're showing the videos embedded in the PowerPoint. I think if each user scrolls over your main image, you will see a pop-up of the controls, and you should be able to press play. Give that a try, and if not, we'll post the movies later.
Okay, sorry about that. Okay, but yeah, so the interesting thing to note here is that the regolith has this very insulating property, and the center of it stays very cool, even though the rest of it, even though there's such a hot temperature source. Okay, and just briefly, since I'm almost out of time, we've also been able to work out an approximate thermal conductivity of the regolith, which is interesting because there just are not many high temperature measurements of this. So we have here is temperature versus depth. So the top of the lava is, the Lava-Regolith boundary is up here. Here's the Lava-Regolith boundary, and these are temperature curves at different times. You can see the symbols are our experimental data, the curves are the numerical solutions, and you can see there's a pretty good first order fit. It's not a perfect fit because we haven't yet figured out the temperature dependence, and thermal conductivity is a very high temperature dependence for different materials. Okay, so with that, just as a summary, we've been able to directly measure the heat transfer from the salt into our lunar regolith simulant, which is pretty exciting, and we've gotten a pretty good verification of our numerical models. To relate this back to the moon, we see that in LROG imagery, there are a lot of areas where you have these numerous layered lava flows stacked on top of one another, and it's pretty likely that between some of these layers, there are going to be some Paleoregolith deposits. So with our modeling, we see that it's probably pretty likely that if we go back to the moon and drill beneath some of these lava flows, we might be able to extract some extralunar volatiles and learn a little bit about ancient solar and galactic history. So thank you. I'll take questions. Sorry if the videos didn't work for everybody.
Great. Thank you so much. And the videos were really terrific when we got them to work over here, so we will take care of this, separate it out, and post it later. I encourage people to go back and look at those. Just beautiful stuff. So I don't see any questions yet in the chat box, but I did want to ask you, how do you think the lava-regolith heat transfer would differ on the moon? Obviously, you weren't doing these things under lunar conditions. So do you have some thoughts on how it would be different actually on the moon?
I guess the primary thing that would be different on the moon is that there's no atmosphere. And so it'd be great if we could do these experiments under a vacuum, but we don't have that technology on this scale. And so I think the primary thing would be, yeah, that there would not be, you wouldn't have the moisture problems that we have, and the apparent thermal conductivity would be lower. If you step out of thermal conductivity, it would definitely be lower because within that thermal conductivity that we've figured out, there is a factor of movement of air within the box. And so that's going to increase the apparent thermal conductivity of the regolith. So that's probably the main difference.
Okay.
The other thing is
I'm sorry, the other thing is what?
Oh, just that our flows are stagnant. We just kind of have an instantaneously in place flow where real lava flows roll in, they continue to move, they inflate, and so real lava flows are much more complicated. This is kind of a simple solution to it.
Okay. Okay, very good. Let's see, there are a couple things being typed in, but I think it's mostly about the movie still. So, yes, okay, so people are trying to help each other to see the movies. Oh, Brad Bailey has a question here in this room.
Hi, I was just wondering if you could talk a little bit about maybe the expected volatile release from the regolith as the lava flow comes over the top, and whether or not you could have any expected, or if you could model that in your lab at all.
Do you mean like on the moon, what would happen to the volatiles?
Please.
Or
so
yeah,
what type of volatile content would you expect in these on the layers underneath the lava flow? Would you expect them to be reduced due to outgassing and the lava actually pulling the volatiles out of the regolith itself?
Yeah, and that's something I have actually wondered, and I've talked to other people about it, and we're not quite sure about that volatiles. You know, I'm not a chemist. I'm not sure exactly what would happen to if they would be reduced on the moon. You know, yeah, I'm not exactly sure about that one. Sorry.
Sure. Just interesting. I'd be curious to see what these drill core samples would look like from a volatile perspective that you were talking about.
Yeah, it's a great question. You've got lots of time to think about it and answer it in the future. So that's good.
Definitely.
Nice question, Brad. All right, and very nice talk. So I think since we do have a question here. Rick Elphick says, volatiles in the lava will exsolve, and some actually migrate into the regolith substrate, right?
I think that's correct. Yeah, I think this is part of the whole question of what happens to the volatiles. You know, what happens to these particles after they're volatilized? Because in a vacuum, they're just going to escape the surface pretty quickly. But then sometimes they're going to be trapped underneath the lava in this regolith layer. I don't think they'll stay trapped for very long. I think the salt is full of holes. It's got a lot of there are a lot of pathways for volatilized things to escape. So I think some of these volatiles will exult from the lava and may probably go into the regolith, but I don't think they would stick around for very long. And the same for anything that volatilizes out of the regolith. It's probably going to be in a gaseous state maybe for a little while, or it might bond loosely to some of the particles down there, but I don't think it's going to last for very long.
Okay, and then Rick adds, but stuff that's volatile at 1250 C is far less so at 150 C. And he puts a little winky face.
He did put a winky face. That's true, and so it might, it might have a weak bond. It might sit, it might condense and sit on the regolith for a little while. But I think that, like if you dumped a glass of water on the moon, it would probably sublimate pretty quickly. And so even if it's not moving around actively, I just don't think it would last very long in a vacuum. If anybody knows more about that, I would love to hear some. But that's kind of been my thought about it.
Well, this is one of those things that if we were all here in person, I'd say, why don't you guys go out and have a beer and talk about it? But you can't quite do that. You can have a beer separately and virtually talk about it.
Should all go to Hawaii and have a beer?
Yeah. No, we'd all like to go to Hawaii and do that. Okay, well, thank you so much, Elise. It was a very nice talk, and I'd like to thank you again for that. Let's thank all of our speakers in this session. And we will see you all tomorrow morning as we start up again, 8:30 Pacific time. Thanks so much for joining today.